Okay, so my research topic is on a surrogate model of the for the optimization of the electrical network of offshore wind farms. And I'll be talking about what I've been working so far and what I hope to do in the following months. So the summary of this talk is, I'm sorry, just to bring it here. Okay. So I'll talk about the motivation, some approaches that are possible for these surrogate models, and the problem definition, how we reduce the problem to make it more tractable, some efforts in data generation for training neural networks, which is the next topic, then some results and the conclusion. The motivation. So we are looking at those array cables, which is on the offshore setting. They link the wind turbines to the substation. This is how it looks like in the real place. And the problem with why do we want to optimize this cable routing is because when you are optimizing for energy generation, energy production, which is a major factor in the economic accounting of a project, you look to reduce the effects of one turbine on other turbines, where you have the wake of the turbine that's generating power. It will reduce the wind speed and generate turbulence. So you want to spread them as far apart as possible to get more energy production and less loads on the blades. But this will increase the cable costs. So at some point, the increase you are getting in energy production is not compensating for the investment cost increase in the length of cables. So the idea is to provide a surrogate model that can estimate how much the cables will cost for a given set of positions, so that you reach a compromise between reducing the wakes and increasing energy, and also not increasing the investment cost too much. So that's the setup. You are optimizing several disciplines together, looking at foundation costs, looking at types of turbines you can do, length of the blades. And at each iteration of that optimization, you provide a new set of positions of wind turbines. And the idea of the system is to generate an optimal layout and give the cost for that layout. But in lacking the optimal layout, which takes some time, we could also get only the cost and leave the layout generation for later, for when you have reached the optimal for the entire farm. Then you have more time to do the optimization for one or a few configurations. But during the iterative process of the optimization, you want something that can just provide the system cost, and if you can, also the gradient of the system cost, the electrical system cost, so that you can guide the positioning of the turbines in the overall framework. So there are some approaches for this problem. There is heuristics, which is fast, but the solutions, you hope they are good, but they don't have any guarantees of quality. Meta heuristics, you get usually a bit better quality, but still it's not knowable how close to the optimal you are, and it can take a bit more time as well. And there is the exact solution with mathematical programming. And this is an NP-hard problem it doesn't scale well with the size of wind farm. And you solve using a MILP model, a mixed integer linear programming model for the site. And the solver used this branch and cut strategy for finding the optimal. But this takes a lot of time. This is too slow for integrated optimization that we want to apply that for. So it has nice characteristics of providing high fidelity and quality guarantees. So it is, if not the optimal, at least you know how close you are to the optimal. So what we are doing is we are using the heuristics and meta-heuristics to start the branching cut, so it speeds up the final solution. But this is only for generating data, because the data is used to train some neural network-based surrogate model. And those solutions will be the ground truth where it learns from. So this is the problem definition. It's the objective function is trivial. It's so we have those binary variables for whether you are linking node I with node j. So x, I, j is 0 or 1. If it's 0, you don't link those two. If it's 1, you link them. And you have weights of those edges, which is symmetric, independent of the direction, but and then you multiply by the binary variable and sum over the entire set of edges. But there are constraints, and that's what makes this problem particularly more difficult. This is already hard. Just doing that is without any constraints would be hard. But you still have these are just circuit constraints, like you want to have all turbines connected to the substation. So you do a power conservation constraint and the single export per turbine, you only have power leaving through one cable. All power reach the substations. But the hard one is the forbidding cable crossings, because it is dependent on what edges you choose. So that would make the problem either nonlinear or with a lot of constraints if you want to really avoid all cable crossings. So we do a problem reduction. What I was talking about is that the variables x and pp is the power delivered from the turbine. They grow with the size of n is the size of the node, number of nodes, n squared. The constraints grow with n to the fourth power. And the search space grows with 2 to the number of variables. So this becomes intractable very quickly. We can do like 40, 50 turbines, but then if you go to 70, 80, if you are lucky, you can get it in a few hours. And if you go above that, it's several hours or maybe days to get an optimal solution. The crossing checks require more than what I showed in the model. It's a bit more complicated. And if you just take the geometric crossing of the edges, you are also preventing some non-straight routing of the cable, which can be used in some cases to the benefit of the cost, to reduce the cost. So we are sparsifying the available edges to choose from, so reducing the search space, allowing non-straight cable routes, and dividing the process in prepare, optimize, and embed. So I'll talk about those 3 steps. So the idea is you have here the initial data, so node positions and the site borders. And what you want to reach is a graph. The graph, which is a tree. So every node, every turbine is connected to the substation without cycles, and respecting the cable capacity. Oh, that's another constraint, which is you can't put any amount of power through one segment of cable. Usually we're working with a given type of cable which have a maximum rated power. So this preparation is doing 2 things. It's preparing how the cables will be routed on site, which is the lower part here, and which turbines will connect to each turbine. So the connection on the topological level is on the top. And then you prepare, you choose the optimal links, and then you embed, you generate the actual routing on the 2D plane. So I'll go quickly how it goes. So that's what you get in a given loop iteration, set of positions. And this site has this additional constraint of not allowing cables on that area here. So If you were going to look at all connections between nodes, you'd have something that goes with n squared. But then we are going to reduce that and use the Delaunay triangulation as a starting point for reducing the edges. And now here we already identify the direct connections that would not be possible because of obstacles in the way. The Delaunay edges alone are not enough to get good quality solutions. So we do an extended set, which adds roughly one more edge per edge of the Delaunay triangulation, which is the diagonal. So for each two triangles of the triangulation, you connect the non-connected nodes together. So that's why it's called a diagonal. And that set is what we are going to work with, but we also allow direct connections to the substation, because in bigger sites, you have smaller strings of turbines, like 5 or 6 turbines that are far from the station, so you need to get straight access to the station. So on top of those, we consider also the star graph. So the substation can also be connected to any node. I didn't draw them because it gets confusing. But it's still a significant reduction, because the Delaunay triangulation grows linearly with the size of the site. And if you add diagonals, you are multiplying by 2, which is still linear. So it's an improvement over using all the edges. The other thing I'm doing at the same time is doing a constrained Delaunay triangulation with the constraints of the site. For example, those concavities in the area. And that will be used as a navigation mesh in the embedding phase, where some links will be realized with a navigation scheme and not directly connecting the turbines. So I'm not talking about the solving process. I'm using branch and cut, but you could use heuristics or meta heuristics. Every kind of solver benefits from a reduced search space. So it still accelerates other approaches. So after the solution, I get this type of result with crossings, because I'm not constraining those crossings that connect directly to the substation. These cables are called the feeder cables, the first one that leaves the substation. And it is beneficial to not block those crossings, because since the topology is a tree, it's always possible to find a path that does not cross. So here you can see that if you go around here, you'd go without crossing. And if you go around the obstacle here, you also would get a route without crossing. So I'll go forward to show how that works. So remember the navigation mesh I showed before? That's what's going to be used now. The actual direct links that are being used, they are mapped here, so they are blocking the path. And then you do some path finding on this thing from the substation to every node. And then for each string of turbines, for each subtree, you just pick the one that requires the least length, and you get something like this. There you see a length already. So this would be the length of the entire site as an arbitrary unit. This is for comparison with a few more options I will show next. This is not looking too good for an optimal layout, but that's because this has the constraint of not branching. So each string of turbines are just a path along a sequence of turbines without any forking, which is usually allowed. So if you allow forking, here, the capacity is 4 here. You only can have 4 turbines connected to the substation on a single string. You already have, but with this relaxing of that constraint or allowing branching, you get a reduction in length. And if you further reduce another constraint that is in effect here, which is use the minimum number of feeder cables. So for 12 turbines at 4 maximum capacity, it would be 3 cables. That's what is reaching the substation here. But if you allow for, you still respect cable capacity, but you allow more feeder cables, you can have a further reduction where you actually connect those directly to the substation and then the others on a cluster of 4 and 2 or 3. So these are the settings that you can tune when you are designing a wind farm collection system. I'm going to use mostly that configuration where you can have, you do have a cable limit, cable capacity limit, but you do allow for more feeders than the minimum possible for that capacity. So now shifting to data generation, I have 83 existing wind farms positions and sites, borders. And this is how they look regarding the minimum distance between turbines, which is a constraint on placing the turbines. You usually have something like 4 blade diameters between one turbine and the next, or 5, depends on the specifics. But and here is the number of wind turbines. So I'm looking at sites up to 200 wind turbines. There are not a lot of very big sites like this. They are mostly on that area. And if I normalize all the sites to have the same area, which is arbitrarily set to 1, then the minimum distance becomes without a unit. So it's just a reference number. Just to have an idea of where I want to generate my random layouts, because 83 is not a lot of sites. I'm augmenting the data with synthetic sites. So I'm using this area here to randomly pick some settings to generate the sites. I'm reserving the actual sites. This is one example. I do solve them with the mathematical programming solver. For different cable capacities, I'm using capacities from 2 to 12, and reserve this for the test afterwards. For the data augmentation, I use only the shape of the sites and the relative position of the substation within that shape. And the turbines, I position them randomly, but respecting the minimum distance. And for each shape, several different number of turbines and several different minimum distance between turbines. Then each one is solved, and this goes to the database. So now moving to the neural networks, one thing, my first attempt was a very engineered approach. So I was looking at creating features that I thought that made sense for the they would impact the total length of the cable layout. So I listed those which are cheap to calculate. So the entire idea is to have it running fast. So it wouldn't make sense to make features that don't have a lot of computation. But they are like things of like distance for nodes, distance to the substation, how much hops, how much within the graph of the available edges, how much hops you have to do until substation, the degree or how many neighbors it has, if it is in the hole, in the convex hole, the outside of the area. Then for the edge, the length of the edge, which is obvious, the angular span, or how much the field of view that it blocks from the substation, in the sense that if it's blocking a lot of field of view from the substation, it's an edge close to substation to generate possibly many crossings. Number of conflicts is the number of crossings. All that talking about the extended Delaunay graph that I showed you. That's where I extract those information from. And then in a global context, the number of turbines and those two numbers are actually some boundaries for the total length. One easy problem to solve is the minimum spanning tree, which is equivalent to connecting every node together without caring for cable capacity. If you had infinite cable capacity, the minimum spanning tree would be an optimal solution for your site. But then you also have the obvious solution, which is just connect every turbine to the substation, which is very expensive, but is also a bound. So it's an upper bound on the worst case scenario of your length and the best case scenario for length. And the optimal will be within those two. So the graph neural network is taking those features, doing a few message passing layers, then aggregate the results, and feed another feed-forward neural network, which uses those global properties I mentioned before. So the feed-forward also sees those global properties, features, and then you get a length estimate. And if you look closer at the message passing layers, there is alternating edge update and node update. And this is very physics-based, so I just did a feature whether the edge is active or is used. And then the node is saying if it is gate, it means if it is connected directly to the substation. And with those two informations, plus the circuit, the power conservation loss, where you have the power arriving at a turbine is also the power leaving the turbine. With those two things, I can get this updating converging to a particular configuration. And then after 5 cycles, I do the aggregation and I get directly a length estimate because I have already which edges are used. So this is a bit of a naive approach, but very, very explainable. So it made sense to me at the time, but I'm looking forward to try less explainable and more effective approaches. So I'm comparing also the graph neural networks that I showed with just a plain feed-forward neural network, MLP, using the same features. And the graph neural networks did not really outperform the feed-forward neural network. But I can get some prediction that is useful. It is around plus minus 5% error. It's not great, but it's meaningful. And if I look at the actual, so this was done with 23 sites. I didn't have the 83 yet, so now I have the complete data, but I haven't yet run the measurements. But yeah, most sites are actually better than this makes you. This gives the impression. It's actually some sites that are particularly bad, and are pulling the dispersion around. But I at least for this one, I know what happened, and I have solved it. So hopefully to improve. Those two are a bit more difficult to solve, but maybe just more data will help. So I managed to get a surrogate model that kind of works, but I want to get more accurate predictions. And now I have more training data, and after getting more accurate predictions, maybe I can dare to get the entire routes instead of just the length, which is a bit more challenging, but would be also a bit more useful. And yeah, there are many graph neural networks architectures still open to explore. I haven't tried everything yet, or even close, just scratch the surface. Oh, there was something. Oh, questions. Okay, that's it.
Thank you, Mauricio. We can take the recording. I invite everyone to take a piece now because we will leave the room at the end of the session. So please do yourself. And we can also invite questions either from the room or online. If you're online,